Shall we start, man? Let the other people join. Coming Monday, I think exam is there. So the syllabus for the first cycle test is first unit. Hope we will complete the first unit. So as usual, it is like the regular 8 marks question, 10 marks question, 2 marks questions. Last time, like just you did, try to write it in paper and then upload in the LMS. Okay. So I didn't still do it. In the meantime, I'll be doing some 2 3 days till it is there. Again, I repeat. Please write something related to the subject, right? So don't bother about the marks. That later we can see. Okay. So we'll start today's thing. This is the second part of the unit number 1. First unit we discussed this adsorption. What are the rate controlling steps? If there is a rate controlling step, how to write the rate expression, all that. So more about it, you will be studying later in the units. Especially if there is a catalyst present, how to write the global rate. If there is no catalyst, but if there is a solid which is being present in the reactant, how to write the rates, how the diffusion plays a very important role. If there is a diffusion, then interparticle diffusion, intraparticle diffusion. Because of that diffusion, how much the rate is being reduced, what is the Thiele's modulus, all that we'll study in third and fourth unit. So we'll leave that derivations there. Now we'll come to one more important thing is, if there is a solid which is being present in a reaction, especially it is a heterogeneous reaction, only solid is there. It may be happening because without a catalyst or with a catalyst. What kind of how to determine this experimental rates? Shell reactor, integral reactor, otherwise called as plug flow reactor, mixed flow reactor, and batch reactor. Out on all these 4 reactors, we assume that there is only one liquid phase is present. At least one liquid phase is present. Rest of the thing may be a solid or whatever it is. Right. So we assume that and then do the calculations. That's what I'll just read here. The following experimental reactors are used to obtain the kinetic data of a catalytic reactions. This type of data are required to determine the rate or rate law parameters, reaction orders, and the rate constants. We'll try to fit the experimental results to one of these 4 reaction equations to fit where it is. Depending on that, we can tell that using a differential flow reactor, this is the expression we got. Using a plug flow reactor, this is the expression we got, right? So before going to that, we'll understand what is this differential reactor. So differential reactor, again, whatever 4 type of reactors, we assume at least only one liquid phase is present. The rest of the thing can be a solid, right? What is a differential reactor? This is a very important 2 marks question. What is a differential reactor? A differential reactor is normally used to determine the rate of a reaction as a function of its initial or entering concentration of the reactants. So if you are using the rate, if you are calculating the rate as a function of initial or entering concentration of the reactant, that particular thing is called as a differential reactant. Here, one assumption what you make is the change in the reactor concentration through the catalyst, because here what you assume in a differential reactor is nothing but it consists of a tube containing very small amount of the catalyst. So very small amount of the catalyst is there in a tube, very small, and the catalyst forms like a thin disc. Catalyst forms like a thin disc, right? Inside, like a piston, small piston. So when there is a catalyst which is small in diameter inside the tube, then we assume that the change of the reactant concentration, which is going through this particular catalyst, that is solid thing, is extremely small. So when you are assuming that the rate concentration outside and inside is extremely small, then we can assume that rate of a reaction is constant at all points inside the reactor. This is one important assumption which you make, because we assume that the amount is very small, catalyst is very small and forms like a thin disc inside the tube. Therefore, the reactant which is passing through the bed of the catalyst is extremely small, the concentration difference. Therefore, since the concentration, inlet concentration and outlet concentration is going to be almost same, we assume that the reaction rate is considered to be constant. So if you use the performance equation, this is just like the reactants are passing through a tube. Therefore, what expression we have to use? We have to use the plug flow equation. Plug flow equation is nothing but V by Fa naught or tau by Ca naught is equal to integral dxa divided by minus Ra. That is for the homogeneous reactions. Since we are having a heterogeneous reactions, we have to put as minus Ra dash. Ra dash when you are putting, that means that it is not based on the volume of the reactions. It is based on the weight of the catalyst. Therefore, instead of V by Fa naught, we put as W by Fa naught is equal to, when you are putting W, the rate also will be star dash, right? So integral dxa by we are getting integral dxa is nothing but the change of it. So we can write as output minus input divided by this. So from this equation, we can get the average rate, because here you are putting as an average. Average in the sense because there is conversion change from inlet to outlet. Out of that, you are trying to take an average, right? So we can get Ra dash is equal to, you put this down, then Xa out minus Xa in divided by W by Fa naught. Fa naught you take it up, Fa naught by W into Xa naught minus Xa in, right? But generally, but generally, this conversion is very small. That is what we are assuming. The reactant concentration is changing very small. Therefore, this almost thing. Therefore, Fa naught Xa out minus Fa naught Xa in, we can write in terms of its flow rates like Fa in minus Fa out. That is the flow rate of A, which is inlet, minus flow rate of A out divided by W. So we can measure this and we know how much is W. From this, we can calculate your rates. Here, one important thing is the average rate will be happening, because here you are putting as average rate, that it will come at the average concentrations. How to calculate the average concentration? This is what Ca average is nothing but Ca in minus Ca plus Ca out divided by 2, because there is not much of changes in Ca and Ca out. That is what you are assuming here. The reactor concentrations are extremely small, therefore there is no difference in it. Therefore, if you want to take an average, you add this divided by 2 will give you the average concentration of Ca. Now we know average concentration. We know Ra dash also. From this particular thing, we can predict what is the rate, right? So what is the stepwise to do? conduct a series of runs using different CA-ins. So different CA-ins, that is CA in the sense initial amount of the concentration of the A, that is A is the reactant, with a series of runs you do, then treat the CA in as CA naught, whichever is CA high CA as CA naught, and use it as the basis for the calculating FA naught. You can calculate XA in and XA out. Once you know CA, we can calculate these two. Once these three we calculate, we can calculate FA naught, W, XA in, XA out, and CA average for each run. Once you do everything for each run, you having different CANs, you substitute in this equation. That is what he is giving. Using 6.66, calculate the reaction rate for each run. You substitute CA in, CA out, the FA in, FA out divided by W. Having different rates you get. Once you get the rates, now you know CS and RAs. We don't know what is the order of a reaction. Then we go for a differential. There are two methods, right? Integral method and differential method. Integral method, you assume some order and then try to fix the parameters. Whereas differential method, what you do, you try to plot minus RA versus concentration data and apply the differential method of analysis of rate to determine the rate thing. If everything is all the points it is for following through it, then whatever rate you are assuming, it is correct. Otherwise, you fix with the some other thing. So here, since we are going for a differential method of analysis, we are naming this equation as a differential reactor or differential flow reactor. So here, anyhow, these two are plug flow only. Since we are using a differential method of analysis, we are calling it as a differential reactor. The other thing is integral flow reactor, where we use integral method of analysis. So in differential flow method analysis, we assume some my RA is K CA power N, then that K and N will be taken from the values of that graph. Okay. That is how we will do the differential reactor. It is just like your differential method of analysis, except instead of V by FA naught, we'll put a W. Once you put W, your RA becomes RA dash. That's only the thing which should be noted. One more thing here is, in differential reactor, the reactor consists of a small tube, a tube consisting of very small amount of the catalyst as a thin thing. Since the catalyst is very small, we assume that the reactant concentration is almost same, right? Once the reactant concentration inlet and outlet is almost same, then you can assume that the reaction rate is constant at that particular thing, right? That is the important assumption. Next, we see the packed bed reactor or integral reactor. Here also, this is also a packed bed reactor. Packed bed reactor is a form of plug flow reactor only, right? So packed bed reactor, some mixing will be there, am I right? Because of intermediate going up and down, right? So here, integral reactor, again, here we assume that the variation in the reaction rates will be along with the length of the reactor, owing to a significant change in the concentration of the reactant. In differential method of analysis, we are assuming there is not much of significant change of the reactant concentration along the length, because the amount of the catalyst is very small and it is formed like a thin disc. That is what we are assuming. But in the integral method of analysis, we assume that the concentration is varying along the length of a reactor, just like your plug flow reactor. That is why we call it as integral plug flow reactor or whatever it is. Since the integral method is used, we call this as integral plug flow reactor. So this method is suited for testing simpler rate expressions, because we know integral method of analysis, we assume some form of the rate expression and try to fix your experimental data to that particular thing. But if the reaction order is more than that, then your integral method of analysis fails. Then we have to go for a differential method of analysis. So this integral method of analysis is used for testing a simpler rate expressions. Here we guess a rate expression. We know what is the integral method. Here we guess a rate expression, whereas differential method of analysis, we won't guess. We fix the rate expression itself. So, and put it to test by the integrating the plug flow performance equation. What is the performance equation for plug flow? W by F A naught is integral 0 to XA dxa by minus RA dash. Here we are putting integral because the concentration is changing. The concentration of the changing along the length of the reactor. Here we are not putting that integral because the concentration is not much changing, very minute change. It is there in the length of a reactor because the catalyst is forming like a thin disk. That is the difference between that and this. Here there will be not be integral. Here you are taking as a integral, right? Rest of the thing is same. So how we do it? Now you see, conduct a series of runs in this experimental with a fixed CA naught, but with the changing W's. So the volume of the catalyst or the amount of the catalyst which you are using, it is going on changing. So keep your CA naught constant and change the volume of the amount of the solids which is in the reactor, or you can change the flow rate also as to cover a wide ranges of W by Fa naught and XA out. Guess the rate expression to be tested. Integrate the plug flow equation minus RA you can put as K into CA and inserting the above rate expression. For each rate, evaluate numerically both sides of the equation, this side and this side. Plot LHS versus RHS of the above equation and test for linearity. We know if all the points are joining in a straight line, then whatever you assumed the reaction rate of a reaction is correct. Otherwise, we test next reactor, what do you call next rate expression, right? That's how we do it. We'll do this in a problem also. At the time, you will be much understanding. I'm just talking about only the procedure, right? This is the integral method of analysis. Even in this particular thing, we can do a differential method of analysis also. In differential method of analysis, your minus RA, you'll put just like that, right? You can see the same plug flow. We can do a differential also. This is more used in more complicated situations, whereas the integral method is used in simpler situations when the rate is order is very small. When the rate is equations are not like elementary reactions, that type we go for a differential. So if you are going for a differential, what we have to do, we don't know this. Earlier we are assuming it, that's why you are putting here. Since we don't know this, we will take this side. Therefore, minus RA is dXA divided by dW by Fa naught. So you are integrating that because since everything is integrated. So dXA by derivative of W by Fa naught. So you are taking different W's, different Fa naughts. Therefore, this can be changed. So what is the procedure for differential analysis in this particular case where the concentration is changing with respect to the length of the reactor? Then what is the steps? Step is same thing. Take a series of runs with the experimental packed reactor with the fixed CA naught, but vary different W by Fa naughts, right? The same like here, vary with the doublet CA naughts. Here, since you are guessing it, here the second step will be not guessing. So plot XA versus W by Fa naught because XA is on the y-axis, W by Fa is on the x-axis. So all the runs you calculate. Then dXA by d is nothing but y by x, right? Y by x is nothing but the slope. So calculate, draw a graph with XA versus W by Fa naught. Then find out the slope. Slope will give you this particular thing. Am I right? RES. That is what is giving there. Plot XA out versus W by Fa naught for all the runs. Then draw a smooth curve passing through the origin because this is y is equal to mx. Therefore, pi should pass through the origin. Then from this equation, it is clear that the rate of a reaction is nothing but differential. Therefore, is nothing but the rate of change with y with the rate of change is x is nothing but a slope of a reaction. Is simply the slope of a tangent of the curve. whatever conversion you want, at that particular conversion, you draw a tangent to that curve, then find out the slope, then we will give you RAs. So based on different XAs, you will get different RAs. Therefore, find the slope of this curve. That is nothing but the rate of reaction by drawing tangents to this curve at a number of XA values. Whatever XA you want at that particular XAs, you draw a tangents. Then you get for a different XAs, you will get different RAs. So and find the corresponding XAs, CA corresponding to the XA. Once you know XAs and you know RA, then you can find out what is this final concentrations, right? So this is the method which is used in integral reactor, especially a packed bed or a reactor, where there is changing of concentration with respect to the length of a reactor. Here, two methods are there. One is integral method. Integral method, you put minus RA and then try to integrate this equation. Whereas in differential analysis, what we do is we try to find out the slope, just like a differential method, what we did in the last semester, right? So that is the next thing. So in this, two things are there. So tablet RA versus concentration data, then test nth order reaction minus RA, K dash, CA power N. K dash and N you can find out from the, take a logarithm and then try to find out from the intercept and slope, right? So that is the second method of analysis, especially the catalytic reactors or heterogeneous reactors. We cannot call it as catalytic reactors. It is heterogeneous reactions where solid is being present as a raw material. The third type is mixed flow reactor. Again, in the mixed flow reactor, the composition of the fluid is uniform throughout. Just like in homogeneous reactions, we are assuming that the mixed type reactor is uniform. With a gas solid system, this ideally is closely approximated as a basket type mixed flow reactor. You can see a basket type. So there will be a basket like a paddles here. So to maintain the uniform concentration, there are some paddles on this particular what you call shaft, so that the concentration becomes uniform. This is the fluid in, this is the fluid out. So whatever is the concentration here, the fluid is going out at the same concentration. Either four baskets you can put or two baskets you can put. That depends on the amount of the solid which is being present. If the solid is more, then if the two baskets are not enough, then put two more paddles so that you get a uniform concentration. That is the thing important here. So the basket, four wire baskets containing the catalyst pellets, right? So this type of a reactor is called as a Carberry reactor because a scientist used this type of reactors, especially mixer reactor. That is why he named that as a Carberry reactor. There is one book, Chemical Reaction by Carberry. It's a very famous book, a very good book also. So, but for your level, it's not required. But remember that there is a book, especially Chemical Reaction by Carberry, James Carberry, right? It's a very famous book. Almost Levensville took a lot of things from the Carberry book. Okay. So how to do this again? What is the plug flow mixed flow reactor expression in the homogeneous? It is V by F naught or tau by C naught is XA out divided by minus RA out. That is what is the expression. Since minus RA dash we are putting instead of V, it is W because we are assuming it is the XA is based on the amount of the catalyst or amount of the solid which is being used. So W minus RA. So rearranging this equation, I can put minus RA out as like this. Now we know what is that. For each run, calculate the rate of exit compositions. You can calculate the exit composition by using 6.7. From this equation, we can calculate exit. So tablet rate concentration data and test its nth order kinetics. For this again, we have to do log because this is the expression which we honor today. We don't know what is K dash and N. So take a log and then calculate its constants like what is the order of a reaction and what is the rate constant, right? So this is same like a mixed reactor, except you are getting W here, right? So next one is a recycle reactor. Just like a recycle reactor in the last semester, we know what is a recycle reactor. You can see here, recycle reactor is a plug flow reactor where some of the product which is there, it is being recycled. Here there will be a mixing. So catalyst is present here. The product is being recycled. So the conversion, everything is based on how much is the recycle ratio here. If the recycle ratio is more, then what will happen? This plug flow reactor will convert to a mixed reactor. And if there is no recycle ratio, that is less amount of recycle, there is no mixing at all. Therefore, it will act like a plug flow reactor, just like what we done in the previous semesters. When recycle ratio is very large, mixer flow is approached. So in the cases, the method of mixer flow reactor, direct evaluation of the rate for each run can be used. If the recycle ratio is more, you can use the same expression. No need of any recycles, right? But if there is a recycle ratio which is in between 0 to 1, that is 0 to infinite or whatever it is, where it is neither a plug flow reactor nor a mixed reactor, then this equation we have to use. What is the equation for a recycle reactor? Earlier itself we discussed that. So that a reactor R by R plus, he didn't give this equation. We can use the same expression like previous homogeneous reactions, right? So the last reactor in this is batch reactor. Again, batch reactor expression is nothing but a plug flow reactor expression. T by C A naught, that is T is nothing but the time of reaction by C A naught is integral 0 to XA, dXA by minus RA. But here we can use instead of RA, that is RAW, then we can put as V by W also. V is the volume, W is the weight of the catalyst, right? So we can use this expression. So 6.12, this is the figure of that batch reactor where there is a uniform concentration. Here actually what is assuming is this particular recycle reactor, it is coming out and you are putting in a batch reactor where there is mixing going on and then sending here. That is what is coming here. You can see there is a rapid circulation and getting uniform concentration here because of the batch reactor. So you can use the same expression here where V is the volume of the gas and minus RA. You can subdivide this particular thing. Minus RAV is nothing but minus RA dash or W, because this expression is based on minus RA, but minus RA you have to put RA dash. Therefore, RA dash is nothing but RA is RA dash V by W by V. So RA, you can substitute that RA dash. So you get V by VW, right? So here the same procedure is being used, except instead of minus RA, which is based on the volume of a reactor, we are putting minus RA dash, which is based on the weight of a catalyst. That conversion, how to change is this particular thing. This already we saw in the homogeneous reaction. Rest of the thing is same, right? So based on these four expressions, we have to do some problems. That is what they will give you in the exam. We'll do one problem now. Yeah, please take down this problem. It's a very important problem. A lot of times they gave in the exam. A solid catalyzed first order reaction A gives R takes place with 55% conversion in a basket type mixed reactor. Find the conversion if the size is tripled. Else, rest of the thing is same. That is temperature, composition, etc. remains unchanged. So write this reaction problem. A solid catalyzed first order reaction. He himself is giving it his first order. Takes place with conversion also is giving 55% conversion. Is giving it is mixed flow reactor. So we have to use the mixed flow expression. Is telling if the volume is increased thrice, if the reactor size is increased thrice, then what will happen to this conversion? Whether it will decrease or increase, right? So we know from our previous thing that if the volume is increased, what will happen to the size of the reactor is increased in the sense volume is increased. If the volume is increased, then there is more amount of time which is spent inside the reactor, the reactants. The reactant spending more amount of time inside a reactor because your temperature, composition, everything remains unchanged. Even the flow rate remains unchanged. Therefore, more amount of time A is spending inside the reactor, more the amount of time A is spending inside the reactor. Generally, more should be the conversion. That is your rough indication, right? So based on that, now the size is tripled, rest of the thing is same. So how to do this by using the mixed type of reactors? All of you wrote this problem? Yeah, the solution you can see. Can we go for the solution now? Yeah, 57 participants are there, excluding me, 56. Vignesh, please take the attendance. Vignesh, I think you can create one Google form here so that they can give the attendance there. You can send a link so that they gives there. Then immediately you can see who is absent. This is my suggestion. That's up to you. Whatever way you are convenient, you do it. Because the other class in EC, what he is doing, that organizer is doing is the coordinator. He is giving a Google form that is in the chat box. Is giving the link. Then all people will respond to it. That based on it, they'll find out who is absent. Okay. It's just my suggestion. That's up to you. Whatever you are comfortable, you do it. Vignesh, you are there? You're not there?
Yes, sir. I'm looking to it, sir.
Yeah. That's up to you. Whatever way you want. But whatever you are giving, it is fine for me. But how you want to do it, that's up to you. Okay. So here we'll see the calculations now. What is that? Here we need to find out how much will be the conversion, right? If the reactor size is tripled, how much will be the conversion in the mixed reactor? Assuming same temperature, composition and flow rate, whatever it is, everything remains unchanged. So let us use this equation. A is giving R, that is what is giving you. It is first order. Therefore, minus RA dash is K dash CA. I am putting dash to tell it is solid catalyzed because he is giving it itself as catalyzed or heterogeneous reactions. So we have to put as K dash. So when you are putting K dash, the rate also will be K dash. So basket type mixed reactor. Therefore, we are taking a mixed reactor performance equation. W by Fa naught is XA out by RA out, right? So XA out by RA is nothing but K dash CA out. CA is based on outlet, right? So here, since A is giving R, he didn't give it is gas phase or liquid phase reactions, only solid catalyst. So we assume since A is giving R, we assume that expansion factor is 0. If he's giving you it is gas phase reactions, then you have to use this expansion factor into picture. Since the moles are almost same, therefore you are assuming it is expansion is 0. Therefore, CA out we can calculate as CA naught into 1 minus XA. So you know what is XA, right? So if you substitute CA out here, then what will happen? W by CA naught. W by Fa naught is XA out by K dash. CA out is nothing but this. CA naught into 1 minus XA. This is the expression which you have to use. Now let us use the case number 1. Case number 1 is 55% conversion. So let the original reactor be W1. Let the second reactor be the other one. Second case will be 3 times that, right? So let the original reactor W is W1 for the case 1. So XA out is nothing but 55% conversion, therefore 0.55. So if you substitute here, then W1 by Fa naught is equal to 0.55 divided by K dash CA naught into 1 minus 0.55. So you are getting one expression 1.22 divided by K dash CA naught. So we can write W1 as like this. We don't know what is FA naught. We don't know what is K dash. We don't know what is CA naught. He didn't give. He is telling that when you compare these two react cases, the rest of the thing is same. That means let us leave it like that because it gets cancelled out anyhow. So from the case one, we are getting the amount of the solid which is being used is this much in that in a factor of FA naught and CA naught and K dash. Let us use the second case. The second case is the reaction. What do you call the reactor size is tripled. So what does that mean? XA is XA or yeah. Now we have to give the kind of conversion in a new reactor. The reactor size is tripled. That means what? Size of the new reactor is 3 times the size of the original reactor. What is the size of the original reactor? That is W1. That is what we assume. W for the thing is W1. Therefore, for the second case, W becomes 3W1. So you substitute in that. This is the expression for the mixed reactor. Substitute W is 3W1. Therefore, 3W1 by Fa naught is XA out by K dash CA naught into 1 minus XA out. We don't know what is this. We have to calculate XA. So we know what is W1 because we already got W1 is this. You substitute W1 there. Yeah, W1 is this. Then do some calculations. We get something gets cancelled out. K dash CA naught, K dash CA naught, CFA naught, FA naught get cancelled out. You are left with 3.66 is equal to XA out by 1 minus XA. So this is one equation which is having one unknown. You can do that, right? So if you calculate the XA out from this equation, it comes around 78.54. That is understandable, right? Because the flow rate is same. Therefore, more amount of the time it is spending inside the reactor. Generally, the conversion will be more. So conversion of A in the new reactor, which is 3 times the size of the reactor, is 78.54. Now, can you do one more thing here? Instead of triple, if the reaction size is reduced to half, then how much it will be reduced? Can you do it now? Find the conversion, the same expression, same problem. Find the conversion if the reactor size is halved. Rest of the thing is remains same. So we know that reactor size is half. Therefore, the conversion should be less than this particular thing. Yeah, please do it and then let me know how much is the conversion, right? So here only one thing which changes is here. This is going to be the same. Only here it will be half, right? Instead of 3, it will be 3 by that is 1 by 2, right? The rest of the thing is going to be same. So 1.22 here, 1.22 divided by 2. So 0.61 it will come. So here it will be 0.61. So if you substitute, how much will be the conversion you do? Instead of 3.66, it will be 0.61, I think, right? Here, because there is no 3. Here divided by 2 will come, because half, right? Rest of the thing is going to be the same. Yeah, there is one more problem which is very important, which comes, you see any question paper of CRE2. This is the problem just they ask. It's a very important problem which has almost, it's like a recycle reactor. It is like a plug flow reactor, all that, right? So what is this, we'll see. Any doubt in the previous one? Yeah. Any doubt? No, I think this boy gave something. Who gave this? Vignesh created a Google form. Good. On for 2 minutes. Good. You are giving the time, Vignesh. Nice. Okay. This is how I think it is better instead of doing all that. Okay. Good. We'll see this problem. The reactant, the results of a kinetic runs. Yeah, please take it notes. The results of a kinetic run on the reaction A gives R made in an experimental packed bed reactor using the fixed flow rate. FA0 is giving you FA0 10 moles per liter. He's giving you, he's changing the amount of the catalyst kgs. According to that, XA will change. So he's giving XA versus W, right? The experimental data. He's asking you, find the reaction rate at 40% conversion. At a 40% conversion somewhere here, what is the rate of a reaction? The second one, what he's asking is, for a feed rate of 400 kilomoles per hour, is giving you the flow rate to large scale packed bed reactor. Find the amount of the catalyst needed for this 40% conversion. For this 40% conversion, if you are changing this flow rate from 10 kilomoles per hour to 400 kilomoles per hour, to get the same 40% conversion, how much of W is required? How much of W is required? That is what is asking you. Second one. Third one is, find the amount of the catalyst that would be required in part 2. This is the same 400 hour. If the reactor employs a very large recycle of product streams. You understood what he is asking you? For this kind of reactors, he is asking you for a 40% conversion with this flow rate, how much will be the catalyst is, how much will be the reaction rate? That is first one. The second one is, if he is increasing this flow rate to 400, almost around 40 times more than the current flow rate, for getting the same 40% conversion, how much should be the volume of the catalyst which is going to be used? That is the second one. Third one is, instead of this plug flow, if I add some recycle to it, again, to get the same 40% conversion, find the amount of the catalyst that would be required in part 2, the same flow rate. If the reactor employs a very large recycle in the sense, what does the reactor happen? It will be like a plug flow reactor, sorry, mixer flow reactor. So he's asking you the same thing, this equation with this, what do you call, experimental result, which you are doing on a packed bed reactor. If there is a recycle very more, that means it is converting like a mixer reactor. What would be the amount of the catalyst for the same 40% flow rate, 40% conversion? So for a plug flow reactor, what is the conversion? What is the amount? And for a mixer reactor at that same conversion and that flow rate, what will be the what do you call, amount of the catalyst which is used? These two are the flow, and this is nothing but the same thing here. So 3 things are there. This lot of times they gave for 16 marks in the exam. Yeah, please try to do it. The solution is here. I'm not taking the solution now. You do it. Try to see this solution and do it. Already this particular thing is put in the website. The LMS, already it is put in the LMS. I'll just show you where did I put. It is already put in the LMS. Now you can see here, this is the notes one, which I showed in the last class, my own notes. And this is the problems. That is what is this, right? This file I put there. So you can go through this because the earlier derivation is I took from this notes, and now the problems and derivations that are expressions I'm taking from this particular thing. So try to see, especially some 17 pages. Out of the 17 pages, I ticked some problems. Please go through that problems, right? So this problem we'll do in the next class. We'll try to have some graph sheet with you, because you have to find out, because whenever they give a data like this, you have to draw a graph. So I'll show you how to how we will be doing here. You can see here, this will be the graph. Then you find out the tangent to it. Then if you project onto the x-axis, you can get one particular thing. And if you project onto the y-axis, you can get what is the W. So the problem looks simple. Only the thing is you have to draw the graph, right? So try to do this problem. And if any difficulty is there, let me know, right? So this problem is you do it in the house. You can go through these problems also, but I didn't put a tick. I'll show you one more problem where you have to do. Yeah, this problem also I put a tick. This problem also they gave a lot of times. Calculate the amount of the catalyst needed for a packed bed to achieve 80% conversion. This is the flow rate they gave. CA naught also is giving you, but he's taking A gives R. This is different rate and one more different rate. So this is based on one rate and this is based on one rate. He's asking you the amount of the catalyst for this particular thing and this particular thing. So you can go through this also. The solution is giving because this is a packed bed reactor. Therefore, you can use a plug flow expressions and then do, right? But here you can see here, since this equation is going to be like this, so it creates some problem there, right? We cannot write CA because this is a second order reaction. We have to write CA as CA naught into 1 minus XA, and then you have to square it, right? That is where the difficulty comes. Please do the derivation and then do, right? Here, you can see here, right? That is one more problem you do because 2 days time is there. You do it, and if any difficulty is there, you let me know, right? And other problem what I want is this. This also they ask a lot of times. This is a solid catalyzed reactions. Gas phase is giving you, unlike since earlier thing we are using as a liquid phase, therefore you are not putting an expansion factor into picture. But when there is a gas phase reaction, you can see A is giving you 4R. Number of moles is increased. Therefore, you have to take the expansion factor into picture. That is why, that is what you will take that expansion factor epsilon A. So you do this problem also because only the equation is different. W, rest of the thing is going to be the same, just like what you did in the previous homogeneous. Try to do it. If any difficulty is there, let me know, right? This is one more problem which you have to do. Again, you have to draw a graph for this. Yeah, this is what he's drawing a graph and then trying to find out the slope to give you whatever is required, right? That is the other one. So 4 problems I showed you here. Please do all the 4 problems. Out of the 4 problems, definitely one problem will come in the final exam. You see any papers, whatever I ticked, 4 problems, one problem out of the 4, one problem, definitely they will ask in the exam. Okay. Be thorough with all the 4. Okay. Other than this, if you are having this Gavane book, this what do you call, scanned copy of a Gavane book, you can use the Gavane book. A lot of problems are there. These problems are there in the 6th chapter. A lot of problems are there. You can go through all the problems and let me know if any difficulties you are having. Okay. With that, I complete this particular first unit. In the next class, we'll discuss about some difficulties, whatever you are having. If you are not having difficulties, then we can go for the second unit, especially what is a catalyst and how to prepare a catalyst and what are the ways of preparing the catalyst and all. Okay. So your first unit syllabus will be till the first unit. Okay. Yeah, I completed my part. Yeah, I ask you to do that 4 problems. Please do it and let me know any difficulties. In the next class, we can discuss about the problems if you are having difficulties. Otherwise, we'll wind off. Yeah, anyone who wants to? Yeah, Sri Vignesh, you raised your hand. Yeah.
Sir, only a few students have filled in, sir. Like 49 response only have come, sir. I think the others are not listening to the class. What to do?
Yeah,
sir?
whoever. Again, boys and girls, please. He is giving you the link. If you are not putting in the link, you will not get the attendance. That tells that you are physically absent there. Okay. So he will give some more 1 more minute time. Please fill it. Otherwise, we'll take only with that particular attendance of that link, not the attendance in the chat box. How many are there? Okay. Okay then. Thank you. Vignesh, you can take and wind off that
Yes,
and give that
sir.
attendance
I'll
of.
close the link now, sir. Yes, sir. Thank you.
Okay. Okay. Thank you.